Hello, hello. I cannot hear you. That's interesting. I'm not able to hear you. Are you able to hear me?
Uh, I
Now I can.
no, you can.
Now I can. Yep.
Okay, okay. So sorry about the difficulties. And welcome. We are very excited to have you with us, and very thankful for accepting our invitation.
My pleasure.
And sorry about the platform. I don't know if it is comfortable for you, but that's all we got.
I would prefer something else, but oh well. We can't change anything. We'll just go for it now.
Sure. I think you don't need any introduction for our students. So without further ado, let's have your time.
Okay. So how do we do
Uh,
sharing
on
this?
On the top, there are a few icons. From the right, the fourth one, you can share a window, a tab, or a screen, or entire screen.
Let's see. Sorry, I need to get going here. Okay. Um, where is it? In all the sharing options, the one thing I'm not seeing is my presentation.
I think the first tab is sharing a tab. The next one is sharing a window, and the third one is sharing your entire screen.
Yeah. To share your window, allow screen recording. Yeah. So they want me to share my window, and then I need to restart Chrome. Okay.
Okay. Thank you for giving it a try.
Okay.
Okay.
Does that work?
Yes, yes. Now we have your screen, the presentation, and it's not in the presentation mode.
Okay. And can you see my mouse?
Uh, can I see? No.
Okay, that's fine. I
Okay.
just want to. All right. So, why aren't you working? What's going on? Oh boy. Okay, weird. All right. So
Okay.
this went to the. Does it say today on it now?
Sorry, I didn't understand your question.
Does the slide say today?
No, no, no. The slide, I think the presentation could be on another window.
Now, what does the slide say?
The slides is just the thumbnails on the left and the big one in the center. I think when you click play, the presentation goes into another screen, and that's the reason it's not shared by the window that you're sharing. Maybe you have to share the entire screen that you're presenting on.
I'm not going to do that. Let's try this. No, that doesn't work. All right, I think I might just have to do it not in presenter mode. Let's see. Okay, so now you see the slide?
Yes, the thumbnails on the left and the big slide on the center.
Okay, we'll just do it that way. All
Okay,
right, so now
okay.
you see today?
Yes, yes, now I see it.
Okay, good.
Okay, okay. So sorry about the technical difficulties, and we're very excited to have your talk.
Okay, my keyboard is not working for some reason. Why is that? Oh, that's why. Okay, here we go. All right, good. Okay, so we ready to go? Everyone's here and listening?
Yes, yes. If anyone have a question, please raise your hand, and I'm gonna open up your mic to ask your question. I'm gonna manage the session with you, Professor. Don't worry.
Okay, cool. Hello, everyone. Sorry about all the delays and the technical difficulties, but we're here at last. So I'm going to talk to you today about open-ended agent learning in the era of foundation models. And what I want to do is tell you about three different types of algorithms that you may or may not be familiar with: quality diversity algorithms, open-ended algorithms, and AI generating algorithms. And then after I introduce them, I want to talk about how these algorithms have really been changed in terms of what we can accomplish by foundation models. Before I begin, I do want to kind of briefly mention AI safety. I think it's a super important topic and one that I take seriously, and I encourage you to take it seriously as well. There are unique issues for AI safety related to the topics I'm going to tell you about today. I won't have time to get into them, but I want to point you to these articles here. We have to proceed really cautiously and wisely with everything we do in AI, especially the kind of stuff that I'm talking about today. So feel free to ask me questions about that if you want. All right, so to begin, there's a paradox in life, which is if you try too hard to solve a problem, you will actually fail. But if you ignore the objective, you're more likely to succeed. So, can you see my mouse, by the way?
Yes, Professor. We have your mouse.
Good. All right. So if you're trying to solve this maze here and you start here and you only incentivize an algorithm to get closer to the goal, which is up here, then what's going to happen is that your optimization algorithm will go north and it will bump its head into the wall forever. And it will never learn to go around and away from the reward signal to solve the maze. In contrast, if you just explore and you ignore the reward, you're much more likely to succeed. Now, that might seem like an overly simplistic problem, but it's actually a metaphor for what happens all the time in science and technology. For example, if you went back hundreds or thousands of years to cooking technology that looked like this, and you said, I will only reward people in my kingdom who are able to do research on cooking faster and more efficiently with less smoke, you would never invent the modern microwave, because to do that, you had to work on radar technology and notice, for example, that a chocolate bar melted in your pocket, and that produces radar, and that allows you to produce a microwave. Similarly, if you went back to the time of the abacus and you only rewarded scientists for making faster computation, more compute per hour, you would never invent the modern computer, because to do that, you had to have been working on electricity and vacuum tubes. And these technologies were not invented for their ability to help us with compute. And so the conjecture here is that the only way to solve hard problems may be by creating problems while you solve them and goal switching between them. So that brings us to this idea of goal switching, which is when you're trying to solve a task A, if you make progress on task B, you should also start working on that other task. For example, if you're a roboticist and you want to work on bipedal locomotion, a robot that can walk, and you start to see your algorithm balance on one leg or crawl on all fours, you shouldn't throw that progress out because it doesn't measurably improve your ability to walk. Instead, you should say, hey, that's an interesting new challenge. Let's try to start optimizing and getting better at that challenge also, because that may be a stepping stone to ultimately getting us to bipedal locomotion. So that brings us to this family of algorithms called quality diversity algorithms, which is wherein the goal is not to produce the single best thing, but instead is to produce a diverse set of high-performing agents or policies. And the canonical and most famous algorithm in this space is called map-elites, which was invented by myself and Jean-Baptiste Moret in 2015. And it's really simple. So the idea here is, imagine that I want to, say, create robots that are really fast. Well, that is my performance criterion, speed. But I might also want diversity in other dimensions like height and weight. So what you're going to do is choose the dimensions you care about, discretize the space, and then run this very simple loop. To initialize it, generate a parameter vector that produces a robot, evaluate that robot to get its height and its weight and its performance, which is shown here in color, put it into the correct spot in the grid that has, put it at the right location, and then you run this loop. Take something out of the archive, change it a little bit, see where it ends up in your discretized space, and if it's the best thing you've ever seen in that location, swap it in. So you keep the best you've ever seen at every location. At the end of optimization, that will return to you an entire set of solutions that will teach you a lot about your space. Where are the the local optima? Where is the best you can do? Where is a place that you can't seem to find anything good, etc. And to illustrate this, we initially tried it on this problem that I had worked on in 2014, where you get all these soft robots that are pretty cool and diverse, but traditionally, we could only get the diversity through different runs of the algorithm. Every single time we ran the algorithm, we got a lot of variations on basically the same theme. Whereas to get diversity, we're running different runs of the algorithm. But that's not what we want. What we really want is within one run, you can generate this explosion of diversity. So look at the difference. Classic optimization produces low performance. Even if you encourage diversity in these two dimensions and performance, which is what people have done for decades, like in multi-objective optimization algorithms, you get a higher performance, but you still don't get almost any exploration of the space. You get trapped on these local optima. And look at the difference that map-elites gets you with the same amount of compute. It's really a sea change in what you can do. Another interesting thing about these algorithms is you can go in and you can take the final solution at any point in the map, and you can say where in the map were its ancestors? Did it, well, the lineage that got to the final solution, where did it visit? And what you see is this like these wild, weird, circuitous paths taken through the search space that ultimately get to a final place. And so what that means is that the system is inventing these counterintuitive curricula. You never would have thought this is the path to get to where that dot is, but that's what ended up happening. So we use these ideas in this Nature paper in 2015 by generating a diverse amount of gates ahead of time in simulation. And then once you have that diverse set, if your robot becomes damaged, you can quickly find a gate that works despite the damage. We also used it in a Nature paper in 2021 in this algorithm called Go Explore, which allowed us to solve really hard exploration problems. These are problems in reinforcement learning where you have to take a lot of actions before you get any reward. Most algorithms can't figure out what to do because they're not getting any reward from the system. And so this game of Montezuma's Revenge was an example of a hard exploration problem. And for many, many, many years, nobody was making almost any progress on this game. It became kind of a grand challenge in the field. You can see all these previous papers here that basically get about zero. And Go Explore blew the roof off this problem, even beating the human world record on it, basically by harnessing the same idea. It said, hey, try to get to as many different states as you can in the game and try to get there in the most efficient and high scoring way possible. And if you do that, that's a way better way to explore a particular problem than what was being done previously. And it ended up solving all of the games of this Atari benchmark, which had been an important benchmark for years in the field. And on robotics, also, if you take the PPO, the dominant RL algorithm, that is intrinsically motivated, so it's also encouraged to go to new states, it still doesn't work. So you need to really harness the principles of these quality diversity algorithms. And that PPO plus intrinsic motivation never solves these robotic challenges where the robot has to put away a toy and it doesn't get a reward unless the toy is all the way put away. And Go Explore solves it in every case. So I don't have time to get into the details of Go Explore. I've given entire talks on that. You can look at my website and see them. The point is, though, is that the principles of quality diversity are extremely powerful and can solve these kind of unsolved problems in machine learning if you harness them. And so I think hopefully I've convinced you that quality diversity algorithms are exciting because they produce a diverse set of high-performing agents, and they harness goal switching, and they do really good exploration. But the question is, what's missing? And the answer is they're still stuck in a single environment. No matter how long you run Go Explore, it's just going to learn to play Montezuma's Revenge better. It's never going to invent a new form of mathematics. And that's because traditionally in machine learning, this has been our paradigm. We pick a domain like Go or StarCraft, and we launch an algorithm at it, and it gets if the algorithm is really good and we put a lot of compute in, it will be good at that domain, but it can't go learn everything, and that's what we really want. And so that takes us to this kind of challenge and subfield called open-endedness or open-ended algorithms that my colleagues and I have been working on for a long time now, basically 20 years. And the idea here is that we want to create algorithms that can endlessly innovate. And I mean endlessly, truly. Like if you gave them 1 billion years of compute, would they continue to do something good with that compute? Would you want to run the algorithm for 1 billion years and continuously check on it throughout the entire course of that run because it's always doing something interesting? And we only know of 2 algorithms in the universe that know how to do this. One of them is Darwinian evolution, which has been running for 3.5 billion years and continues to surprise us. And the other one is human culture. So science doesn't end. It continuously invents new challenges, new technologies, new solutions, and every one of those solutions creates a new opportunity for new investigations. And so, for example, in Darwinian evolution, evolution created the problem or the opportunity of leaves high up in trees, and then the solution in the form of caterpillars and giraffes. And then giraffes and caterpillars are now opportunities for things to eat them, live inside them, cooperate with them, etc. And so there's this endless cycle of inventing problems, solving problems, etc. And so we created an algorithm in 2019 that tried to capture the spirit of open-ended algorithms. It was called POET. And the subtitle here is Endlessly Generating Increasingly Complex and Diverse Learning Environments and Their Solutions. And the way that it works is the following. We're going to, and this was a first at this time, create a parameter vector that describes an environment. Okay, so now we're searching for the environments, not just the agents that solve the environment. And what we're going to do is have the start with a random parameter vector, so a simple environment. And then we're going to start growing a set of environments. And periodically, we will take an environment out of the population or the archive, change it a little bit. And if the resulting environment is not too easy and not too hard for the current set of agents, and it's novel, we'll add it to the archive. And then we'll just loop. We'll continuously generate more and more environments while also optimizing agents to solve those environments. And critically, we're going to allow goal switching. So if an agent is currently working on one environment, we're going to periodically check it to see if it's good at another environment. And if it's the best we've ever seen at that other environment, we'll copy it and let it kind of invade that niche. And now that solution might be the thing that unlocks a lot of progress in that new environment. That may in turn allow it to switch to some other environment, et cetera, et cetera. So just like species in evolution can hop from niche to niche to niche, our agents can now do that in an ever expanding set of environments. So this algorithm produced a lot of really interesting results. So it starts off with really simple environments, one kind of challenge like stumps or a little bit of rugged terrain or gaps in the environment. And over time, the system automatically makes more and more complex environments. And ultimately, everything that you see here has produced by the algorithm itself. And it started to really produce combinations, big gaps, big stumps, lots of rugged terrain, all automatically produced by the system. This is a slightly different version of the algorithm, but all of the environments you see here and the learned agents are all produced in one run of the algorithm, exploring the space of what is possible, which is really, really cool to see. And in one of my favorite plots in my entire scientific career, here is a phylogenetic tree of environments as they're generated, each of which was solved by the algorithm. And you can see, just like in nature and human technology, this like sustained diversity. You've got like the big cats, the dogs, the reptiles, the fish, and then lots of diversity in them, or different branches of science, mathematics, culture, technology. A lot of really kind of persistent, sustained, deep exploration of the space. Another group basically took our idea, did it in simulation to train a generalist agent that then, because of domain randomization, because it trained in so many diverse environments, was able to go and do really complicated things on a physical robot in the real world, which was super cool to see. So I hope I've showed you that POET demonstrates the benefits of quality diversity and generating environments while you try to solve them. However, POET itself, while it can automatically generate tasks, is still also stuck in a hand-chosen distribution of environments and tasks because we had to pick that environmental search space that we parameterize, so it still is not going to go invent an entire new form of mathematics. So let's take a step back and say, hey, if we want to produce artificial general intelligence, which is like whether we should do that is its own conversation. But if you want that as your goal, then we still have a long way to go. And the question is, how will we get all the way there? And that brings me to a paper that I wrote in 2019 that proposed this idea of AI generating algorithms. And the basic observation here, the basic observation here is that there is a trend in machine learning that basically hand designing the solution is not the best way to go about producing really impressive algorithms. Instead, we should kind of try to go all in on learning and try to learn the entire solution. And there's an existence proof of that working on Earth, where we spend a lot of compute on the planet Earth to ultimately produce you, the human being, the most sample efficient learner that we're aware of. And so if we want to automatically use machine learning to produce really powerful AI, I think we have to simultaneously push on 3 pillars. We have to learn the architectures, so architecture search. We have to automatically learn the algorithms with meta learning, pre-training, in-context learning, things like this. But we also have to automatically generate effective learning environments. And so we don't want to be manually designing each of these pillars. We want to be trying to just throw a lot of compute at them and let machine learning do the heavy lifting. So far, I've focused a lot on this third pillar, generating effective learning environments with QD algorithms, open-ended algorithms, and POET. But today, I now want to switch our attention and say, is there something new that we can do now that we have these things called foundation models that can really turbocharge our algorithms? And as you can imagine, the answer is going to be yes. So the first work I want to talk about in this space is called Omni, Open-Endedness via Models of Human Notions of Interestingness, done by Jenny in my lab here with Joel and Ken. And the idea here is that, hey, POET was trapped in one narrow distribution of environments that we hand chose. We want to break out of that. So we need to search, if we want to produce a truly open-ended algorithm, we need to search in a open-ended search space, a truly vast space of possible environments. The problem is that if you open up the space of possible environments to basically everything, well, now you've got a needle in a haystack problem. Most of the environments in that space are totally garbage. They might be impossible to solve. They might be nonsense, too hard, too easy, etc. So what we really want is that every new task we train on is both new, but also interestingly new. And the question is, how are we going to find those environments? And so the first challenge is that we want learning progress. We want to know that the problem is not too easy and not too hard. Well, we can use some techniques my team developed at OpenAI and some other challenges. The problem is that even if you always are learning, it might not be an interesting form of learning. For example, if you take a random string of numbers, or pi, you can always memorize the next 10 digits in the sequence of numbers. So you'll always have some learning progress, but that's not interestingly new learning, right? We don't want to learn for a billion years arbitrary digits of pi. What we want instead is to be working on interesting new challenges, just like science. When you submit a paper to NeurIPS, they judge whether or not what you're working on is interesting. The problem is people for 20, 30, 40 years in computer science have tried to hand code what counts as an interestingly new thing. But every time you try to do that, you try to quantify what counts as interesting, and then you optimize against that measure, you end up getting all sorts of pathological garbage. For example, if you tell a robot, hey, try to always find a new state, a new observation, well, it might just watch TV tuned to static forever. If you tell a robot, hey, always produce a new configuration of your motor, your joints, it will just twitch in random ways forever, which doesn't give us exactly what we want. So this relates to Goodhart's law. When a measure becomes a target, it ceases to be a good measure. And so I don't think we can hand code what counts as interesting. We have to do something else. And what is interesting? Well, as Justice Stewart said, we can't define it, but we know it when we see it, which is to say that humans have a notion of what counts as interesting, but we don't know how to write down code that can tell us that can capture what we do in our function of interestingness. And so this kind of ends up being the most important problem in open-endedness. And so an answer is, hey, we can just ask foundation models. So foundation models already know what is interesting. They've read the entire internet, including lots of people talking about what counts as interesting versus not. And they also have common sense. So we can just ask them, hey, is this thing I'm proposing to do, does that count as an interesting new challenge? And so that leads us to this work on Omni, where we're going to try to have open-endedness, but with a model of human notions of interestingness that is inside of the foundation model. So we're going to have reinforcement learning. We're going to give it a task. So try to do this, try to do that, try to do this. And when we sample those tasks, we want tasks that have high learning progress. So the agent is not yet good at them, but can become good at them by training on them. And also that task should be interesting. And so we're going to, for learning progress, we're going to use this technique that was invented by my team at OpenAI and Ingmar in particular. That works quite well. I'll refer you to that paper for how we calculate learning progress. But for the model of interestingness, that's the new part, we're just going to ask GPT. We're going to say, hey, here's all the things we've done so far. This agent has learned so far. Here's a new proposal for a task. Is that task interestingly different compared to everything the agent has already tried to learn? And the results are that if you just do uniform sampling of tasks in either of these domains, that's the red line, that you don't get much progress. If you use learning progress alone, you still do pretty well, but you start to spend a lot of time on tasks that are learnable but not that interesting. And so you don't do that well on a held out set of tasks that humans curated as interesting in this domain. And if you use Omni, that's in orange, you do even better because you spend your time focused on more interesting tasks. Now, those two domains, we still were in a pretty narrow task search space. So we wanted to open it up and say, hey, let's go to an infinite task space. Specifically, we wanted the space of all tasks specifiable in natural language. So anything you can ask the robot to do in some complex domain like this kitchen. For example, take a knife and put it in the toaster, like pour water in a toaster, take the toaster and put it in the garbage, anything you can ask for with words. The problem with that is that now you need to be able to automatically judge for any task that I just made up, did I accomplish that task? So if I say, throw the toaster through the window, I need to know if an agent actually did that in order to launch a reinforcement learning algorithm that will train it to accomplish all these tasks. So you need what I call a universal reward function to do that. And we tried a VLM, a video language model, to just watch the video and tell us if it accomplished it. I think that ultimately that's the right answer, but that didn't work for us. So for now, we just had the system automatically write code to use the state of the world to check, is a knife in the hand of the robot? Is the toaster in the sink, etc. So now we have an infinite task space, automatically generating interesting tasks and automatically judging if those tasks were performed. And in this space, if you do uniform sampling of tasks, you get nowhere. If you use learning progress, you also get nowhere because the space of tasks is too big. You're spinning your wheels on an endless stream of uninteresting tasks. And if you use Omni, you do much better over time. And interestingly, Omni creates a really good curriculum. So first it picks up an apple, then it learns to find and pick up a knife. And later on, it's like, oh, let's use the knife on the apple to slice the apple, and et cetera, et cetera, et cetera. So a pro of Omni is we're now in an infinitely big task space. The con is we're still kind of trapped in one type of environment. We're just in a kitchen forever. What we really need is this idea that I introduced in my 2019 paper, is a Darwin complete environment search space, which is to say a search space that has any possible environment. So we can do what Darwinian evolution did and produce, dolphins and whales and birds and humans. And so the idea of this Darwin complete search space is, can we express any environment that you could compute on a computer? And I've so far only thought of two, and I have a project with collaborators on each of these. The first one, which came to me more recently actually, is that, hey, code itself is Turing complete, and therefore it's Darwin complete. And so we can just have language models literally propose new environments in code where they produce the environment and then we operate inside it. And so that leads us to the follow-up to Omni, which was Omni Epic, which is, hey, let's have Omni just literally create environments in code, and that will thus get us a Darwin complete search space. So GPT can write code. In this case, we asked it to write code within this PyBullet simulator, but it could have written its own simulator or used many different simulators. It could even create logic tasks. And so every environment here you see here was produced by GPT, and then the agent learns to solve it. So first the agent jumps from platform to platform, and then it creates space. It has platforms that go up and down. Then it can kick a ball through goalposts, and then it can jump up, basically deal with platforms that move up and down. Let's see what else. It eventually creates a more complicated obstacle course here. Then it does something cool like touch a button that opens a bridge and runs across it. And so there's this endless stream of really cool environments where the agent is being asked to do stuff. But now the space is just vast because there's any code you could write for a computer that could become a task for the agent. And if you basically run this thing for a really long time, the more compute you give it, the more diverse tasks you get. So you get like search a building, climb different kinds of stairs, kick a ball off the wall of a building, a bank shot, soccer drills, football drills. It even creates a construction site that needs to be cleaned up and a busy restaurant with dishes on the table that needs to be cleaned. So this is pretty exciting. For like the first time, we're basically finding a situation where no matter how much compute you pour at the environment, you get more and more and more amazing stuff. And so we're starting to get algorithms that maybe we should actually run for a billion years because maybe they'll do interesting things. Who knows? We don't know the answer to that. But we're starting to have algorithms that would be interesting to run for a really long time. And that I think shows a lot of progress in the field of open-endedness. So to give a conclusion to this mini chapter of the talk, Omni allows open-endedness via models of human notions of interestingness. It finally enables us to focus on interesting tasks because foundation models have learned that ineffable concept of what it means to be interesting from human data. And then we have Omni Epic, which can generate any possible environment using code. So it's Darwin complete. And I'm really excited to see what would happen if you just scaled Omni up. So I mentioned that there's 2 Darwin complete search spaces I'm aware of. We already talked about code with Omni Epic. The original idea I had in 2019 for what might be a Darwin complete search space then seemed like a total fantasy. It seemed like crazy to even propose. And I even was worried that people would like think that I was literally crazy and like laugh me out of the academy and think that I wasn't like a researcher worth talking to because I was proposing these science fiction ideas. And the idea was, hey, in theory, you could just take a neural net and have the neural net generate the initial state of the world. And then you give it an action and it tells you the transition function. It says, okay, here's the next state of the world. And you enter another action and it's like, here's the next state of the world. And effectively the neural net could be the entire world. It could simulate in theory, because it's Turing complete, it could simulate any video game, any physics simulator, any logic problem, math problem, coding problem, text problem, whatever. It could do all of that because it can just produce visual or even send other kind of modalities as like its observation, and you take any action you want. In 2019, that seemed completely and totally laughably crazy, but fast forward a few years and it turns out you can do this. And this is unbelievable. So this leads us to this project from called Genie at DeepMind that was led by all of these wonderful scientists. And the idea here is that you can literally create a world model in a neural net that can generate any possible environment, like a video game. And you can condition the world model to do whatever you want. So you can ask it with text or with an image or with a drawing, hey, I want this kind of a world, and it will just be the transition function. You give it an action, it goes to the next state, the next state, the next state. It seems like this is too like impossible, but we actually showed you can do it. So here's one way to use this model. You give it text, like screenshot of a world with a warrior protagonist. Imagine, or in any image generating model, produces that image for you. And then you give that image to the world and an action, and it gives you the next state of the world. You give it another action, it gives you the next state of the world and the next state of the world. And here is a video of that working. So we started with 2D platformer games in Genie 1. And so you give it an initial image and then you can play the little character. It has to figure out what is the thing that should be controlled by actions, what is the character in this world, and then you can actually play it. And it's kind of blurry and it doesn't last for very long, but it gives you a sense of what's possible in all these 2 different platformer games, which was pretty incredible to see. What's also true is that these are basically foundation world models. And so they have scaling laws. The more you scale them, the more compute you give them, the bigger the batch size you give them, the lower your loss, which is what's here on the y-axis. And that is a good sign. It means that probably, even though Genie 1 was just these blurry little images, maybe Genie 5 will be mind-blowing. These are actually drawings made by my children, and they created a world with markers, and then you can step into that world and control the characters that you've created and explore and play your world, which is incredible. You can also have robotics. So here, the robot, this is a fictitious robot entirely imagined by the world model, and it learns all sorts of cool things like how to move and operate inside the world. Now, because these things are very similar to world models, then you get a lot of the same properties. They're general, they can generate any environment. You can build upon them. You could fine tune them with more data. You could RLHF them if you didn't like how they were behaving. They get better with more compute and data, etc. So to demonstrate that, an expanded team actually went and just basically threw a lot more compute and a larger data set at Genie. And so, we changed the methods a little bit, but Genie 2 is basically the same idea, but now bigger model, bigger data, 3D worlds, and look at all the crazy stuff you can do. So here it knows if I touch a door panel, it should open the door. If I start in this city here, I should be able to control the robot, and robot locomotion looks a lot different than driving a boat, for example. Here it knows that forward moves the boat forward, whereas forward on a robot has to swing arms and legs, and you can create water worlds, forest worlds, sand worlds, anything you want. This huge diversity of three-dimensional environments. And you can also show that different actions result in different things. So here we created these three doors, and one of them has this kind of fantastical garden, another one's a staircase, and here we say to the agent, go through the left door, and it walks in, and you get to see there is in fact some sort of Garden of Eden kind of vibe in that thing. Over here, you can ask the agent to go through the center door, and the world looks different. It's some sort of cave that is being explored. And also here, Genie will invent a staircase if you ask it to go through the door that has stairs. And there's there's some upstairs that you can go visit. All of this imagined with inside a neural net. So that crazy dream I had in 2019, actually now you can see it right here, all these different worlds. Here, you can control an agent to either go forward, go left, go backwards, jump, and those same actions are consistently able to be done in a different world. Go forward, jump, etc. You can even interact with objects, like blow up this barrel of explosives. You can go slash a balloon with a sword. You can drive a boat around, etc. Very crazy. Also, I want to just have you think, this is the worst this model will ever be. Really stop and think. You saw the jump from Genie 1 to Genie 2. What does Genie 10 look like? Just enjoy that thought. So imagine if we start training agents like Poet style or Omni style, but now in Genie 10. Even Genie 2 would be exciting. You can learn all these totally different skills in a never-ending supply of environments. So I've really spent a lot of time expanding out pillar 3 of my AI generating algorithms here. You've got quality diversity algorithms and open-ended algorithms like Poet and Omni Epic. And now we've added Genie as another potential source of endless environments that you could use to train your agent. Now, I want to kind of end the talk on pillar 2 here. So now that we know how to generate environments forever, we now need to think about how are we going to efficiently learn in these environments. And so that brings us to this project I did at OpenAI called Video Pre-Training. And the idea here is that even if you can generate endless environments, reinforcement learning often doesn't do very well if the problem is too hard to explore, it's too hard to learn in. And this is kind of a tax on open-ended algorithms, because if I keep suggesting environments that are interesting, I might have to spend so much compute learning in them that everything slows down, and I might not even be able to explore very well. So in theory, you could use exploration techniques to learn each new environment. But if that takes a lot of compute and time, that's just a tax on the whole system. It slows everything down. So could we speed up these algorithms? Another way to phrase this is, can we make AI generating algorithms without a planet-sized computer? I think the answer is yes. And to borrow from Newton, that's because AI sees further by standing on the shoulders of giant human data sets. We can use internet pre-training to speed up the ability to learn within these open-ended algorithms. And as an example of that, we decided to test our agent to see, can it learn to use a computer? Can it use a mouse and keyboard to do what humans do on computers? Our example task was Minecraft, because that is a video game that people spend a lot of time on, and there's lots of internet videos online of people playing. And so we want to try to do pre-training on just by watching videos of people using computers, in this case to play Minecraft, and therefore see, do we become more efficient at learning hard tasks in Minecraft? Does an agent become more efficient? A challenge is that videos are unlabeled. So unlike text and music and images, where you get the next word or the next note or the next pixel for free to do self-supervised learning, with videos, you don't know what actions were taken at every time step because you're just watching the person play. You see the results of their actions, but not their actual actions. So what we did is we just trained a model called an inverse dynamics model that just learns to predict what action must have been taken between the past video and the future video. For example, if you see this frame and then this frame, you know the agent must have hit the jump button. Once this IDM model, inverse dynamics model, can figure out what action must have been taken, then we can go to vast amounts of videos on the internet and infer what action was taken. And now we have labeled data. So now we can just do behavioral cloning at scale to say, hey, conditioned on the past, what action would a human take in this situation? And how about this situation? And then you can auto-regressively roll out this model in a new world, and it'll act for you. So we trained on about 8 years of video through a lot of compute at it, and we see scaling laws. So the more compute you throw at it, the better you do, zero shot. But only when you have tremendously high levels of data do you start to see the agent be able to do things that humans take about 2 minutes and 3,000 actions to perform. And I want to show you this really amazing video here. I'm going to call your attention to the right one. If you pre-train and then do a little bit of fine tuning, and then you release the agent in a world, then look at what happens. This agent is exploring this village, and it's doing a very efficient job of exploring this village. It enters one building, opens a door, checks it out. It goes and it knows how to climb stairs or open chests, and basically systematically can explore this village. That is the kind of pre-training you need to quickly be able to learn what to do in a new environment. In contrast, typical neural nets they don't know how to see, they don't know how to move, they don't know what a chest is and that you should open it, what a door is and that you should open it, what a staircase is and that you should climb it. So if you pre-train on human data, you are therefore primed and ready to learn a new task. And to test that, we gave our agent this really hard task, which was a grand challenge at the time in RL, which was getting a diamond tool in Minecraft. This takes humans on average 20 minutes and about 24,000 actions. And what we showed is that if you do not pre-train, that's this blue line here, and you just do reinforcement learning, giving a reward for each step in the process, it learns nothing, almost nothing. However, if you pre-train on the internet and then you do reinforcement learning through this stage of tasks, you systematically learn every next step in the ladder, the tech tree, and you ultimately do accomplish this goal, which again takes a skilled human over 20 minutes and 24,000 actions on a computer, which is just incredible. So here's a sped up video of our agent at work. It does all these really hard tasks that humans know how to do. It even knows how to drag and drop little icons in a specific way to kind of craft things in Minecraft. It's learned to drag and drop and click just like you might learn to use a computer in Microsoft Word or Excel, etc. I won't be able to show you the whole 20-minute video, even sped up, but you can kind of watch this agent just extremely skilled at accomplishing things in Minecraft. Here, it's mining the right resource after burrowing down into a cave. It then knows how to make a crafting table, to make a tool, to make a furnace, and then it knows how to like put the wood and the material in the furnace in exactly the right way to start like making iron, crafts iron tools, which eventually allows it to go and figure out how to find diamonds. Pretty incredible. So the conclusion of VPT is that by pre-training on the internet, our agents can stand on the shoulders of human data, on giant human data sets, and learn how to act, to see, to think, to know what languages, etc. That allows them, when we put them in a new environment, to be very efficient and start learning things that otherwise you wouldn't be able to learn. And if you pair that with open-ended environment generation, now I could learn the next task and the next task and the next task more efficiently. That would allow us to basically like start agents at our current skill level or near human level skill, and then let them go and explore and learn forever and go way beyond what humans are capable of doing. A more recent kind of iteration of this idea is in the SIMA project at DeepMind, where you have one agent that's language conditional, but it can act in like 13 different complex video games. So not just Minecraft, but all these video games. And one of the most amazing results of this project is that if you train in like 12 complex modern video games, you generalize to the 13th video game about as well as if you had just trained on data from that environment. So we're starting to see really general agents that can go to a completely new environment and solve new tasks that they were not trained to do because of pre-training. And in fact, earlier when I showed you these three agents here that were going to different things, and they were able to take a text instruction and either go through the left door or the center door or the right door, that was the SIMA agent actually off the shelf paired with the Genie environment generator. So now you have a world model pre-trained on the internet, an agent pre-trained on the internet, interacting to do really wonderful things. And that's kind of what I'm trying to tee up in this talk. Foundation models have allowed open-ended skill learning in a way that just seemed crazy and impossible in 2019. So to conclude this part of the talk, VPT and SIMA, by pre-training, enable learning really hard exploration tasks efficiently, and that can be paired with open-ended environment generation, which is pretty exciting. Okay, I want to quickly tell you about, I think, 2 more projects, and then I'm going to conclude, actually 3 more projects, and then we'll quickly conclude. So the first one is the automatic design of agentic systems. This was done by Sun Ren here. And the idea here is that increasingly we don't just use an LLM with a prompt that gives us text. We increasingly use what we call an agentic system. It might be able to do a web search, interact with users, reflect chain of thought, reasoning, all this stuff. And these agentic systems, which are kind of like a wrapper around a language model or like a flow chart that has multiple calls in it, they're hand designed. And if you look at all these complicated agentic systems that are being designed, they require a lot of manual effort. So why not take the AI generating algorithm philosophy and just have machine learning learn to generate these agentic systems? And we'll use the principles of open-endedness, which is a growing archive of stepping stone ideas that we kind of look at, build on, change a little bit, just like scientists do, but automated. You could even use Omni to say, what's the next interesting agentic system? How about the next interesting agentic system? And if you do that, you can therefore have an automatic system that is searching and producing, new agentic systems in a Turing-complete language. And you just basically repeat the same idea, grow this archive, try new things, test it on problems that you think are interesting. And over time, this agentic system gets better. So here are all these dotted lines are hand designed agentic systems, kind of state of the art things like chain of thought, reflection, etc., debate. And here is our agentic system. We call this the automatic design of agentic systems, or ADAS. And ADAS over time just gets better and better and better, and ultimately produced this particular agentic system, which was on the problem we were trying to solve way better than all of the hand-designed state-of-the-art things. So now you can launch a search algorithm, which will automatically go create an agentic system tailored to your particular problem and solve it really well. Of course, if you trained on a massive distribution of problems, you would get a general agentic system that's just generally good on any problem. And we've tried it on math domains, non-math domains, etc. I want to remind you that we need to be very safe. We did a lot of safety protocols. You can look in our paper to see them. We need to make sure we do this stuff in a very safe way. So do not do this work if you're not willing to put in the time to do it safely. Future direction, which is we're actually working on now, is having the agentic system improve itself so that every time it makes an improvement, it gets better at making the next improvement and kind of get better. You have self-improving AI that gets smarter and smarter. Again, you need to do that safely, but it's very exciting. So that concludes that little mini chapter. I also want to talk about the AI scientist, also done with this amazing team of people. And here the idea is that we want to automatically do science. So in some sense, the most open-ended domain imaginable is what scientists do, which is trying to make new discoveries in the world of machine learning, of biology, of chemistry, etc. So could we actually automate that search process? And the answer is yes. So we chose machine learning as our domain because there the computer is the actual world. And but you could apply it to other domains like chemistry and biology if you had an automated lab. So the AI scientist, it generates ideas, its own experimental, like what is my research hypothesis? What's my paper going to be about? It designs and runs the experiments to test its hypotheses. It analyzes and visualizes its results. It creates plots, charts, whatever. It writes the entire scientific manuscript. So this is a paper here entirely generated by the AI scientist, conducts its own peer review. And if it thinks a paper is good, it can publish it to its own internal archive. We haven't actually done the next step, which is then let it kind of read its archive and build on its own discoveries. But it's all set up to do that. We just need a lot more compute. And so here is this overall workflow. You can stare at this offline if you want for how we actually pulled this off. But what you do find is that it is a pretty good reviewer of its own work. It's about as good as humans at kind of doing review. And it can write a whole paper, which is pretty incredible. And if you look quantitatively at the results, the scores it gives its own work are not as good as human papers, but it's kind of getting in the ballpark of human papers. There was even an example where the AI scientist produced a paper on an idea. I read the paper and I was like, that's actually a really good idea. I'm surprised how good it is at creating this idea. And like 2 months later, a human team of scientists published a paper on exactly that topic, showing you that the AI scientist is, in some sense, producing ideas that humans themselves find interesting enough to dedicate a year of their life working on, and then the community is excited once that idea gets published. In V2 of the AI scientist, which we just put online about a month ago, what we showed is that we generated a paper that was actually accepted by peer review at a workshop at iClear. So it's kind of currently able to automatically do workshop level machine learning research at a top tier conference. So you can look into V2 if you're interested. We have a whole blog post on it. It's better than the V1, but I want you to think not about V1 or V2, but V5. Where we're headed is basically potentially automating scientific research and therefore rapidly accelerating what we can discover and learn about the world. And maybe we can do things like cure cancer and amazing, things like that if we automate all of science. Again, I want to be really clear that there's a lot of safety and ethical issues. We talk about them at length in the paper. I encourage you to read that. We took a lot of safety steps in this work. You should too if you're going to work on it. But I really want you to think about how good this is about to get. So we've seen in image generation, you can go from these images in 2014 to these images 10 years later. And the same thing is going to happen for everything I've talked about in this talk. Genie and world models, SIMA and pre-training, the AI scientists, the automatic design of agentic systems. It's all going to get better crazy fast, which is just wild to what we're about to witness. Okay, so in future work, we want to scale this way up. We want to do it on different domains with better models. But really what I'm most excited about is doing it in an open-ended version where it basically publishes papers to its own archive of discoveries, reads them, and does the next thing and the next thing and the next thing. I think that's going to be terrifically exciting. Okay. I'll actually, yeah, I think I'll just quickly do this one last paper and then we'll go to Q&A. So the last thing I want to tell you about is this work called Thought Cloning by Shinran here. And basically the idea here is that we want to have our agents learn to think while they act by imitating human thinking. So most AI agents, especially ones in like 3D worlds, like learning to play Minecraft, they're not thinking in natural language while they're acting. But if they did, they'd probably learn to perform better, generalize better, have all the magic of human performance, because thinking is what makes humans so powerful, right? And so the idea in thought cloning is that we're going to imitate how humans think while they're taking their actions. So if you think about VPT, we just trained the agent to act like a human in every situation. We didn't train it to think like a human before it takes that action. That's what thought cloning does. So typical behavior cloning, you just train the agent to take an action, the same action that the demonstrator did. In thought cloning, we want you to think like the agent did and then take the action the agent did. So we need access to some data set that has a bunch of human thoughts behind each action. To do that, we created a synthetic data set because we didn't have massive thought data. But what we show is that if you do that, if you are forced to think like a human in addition to act like a human, that's blue here. You learn way faster and reach a higher total performance than if you just imitate human actions, which is pretty cool. You also generalize way better out of distribution. So in distribution is on the left, out of distribution is on the right. If you just learn to imitate behavior, then you start to fall off a cliff as you get out of distribution. If you have learned to think like a human, you kind of degrade your performance more gracefully with a massive performance difference as you increasingly go out of distribution. That's zero shot. And then here we show fine tuning. If you fine tune an agent that was trained with behavioral cloning or imitation learning, it does get better if you fine tune on a new data. But if you fine tune a thinking agent that learned to think like a human, you get actually a much bigger lift when you're way out of distribution and higher performance. Okay, what's also cool is that the agents are interpretable. You can like watch them think. And so if you see your robot is stuck at a door, you might not know why. And if you don't know why, you don't know how to fix it. But if you see it thinking, it says, oh, I can't open a door because there's a person here. And you're like, oh, it doesn't know that posters are not real people. They're pictures of people. And you might want to add some posters to your training data. You can also stop the agent if it's about to do something really unethical or evil. So if the agent says, hey, next thing I'm going to do is rob a bank, then you could stop it from doing that. And as a quick demonstration, we basically took an agent that was trained. And then afterwards, at inference time, we decided, hey, touching red things is bad. And so if the agent tells us it's about to pick up a red thing, we just stop the program. Well, you see a massive reduction in the amount of red things that are touched. And so it shows you that one of the benefits of knowing how, like having interpretable thoughts in your agents is that you can make them much more safe in addition to more debuggable. Okay, 3 conclusion slides for the whole talk. I've introduced quality diversity algorithms. They explore well, they create and collect stepping stones, they harness the idea of goal switching in these counterintuitive paths, and curricula get invented. I've introduced open-ended algorithms, where the goal is to create algorithms that truly endlessly learn and innovate forever, like natural evolution and human culture. And I've introduced AI generating algorithms, which is basically the ideas of open-endedness, but specifically pointed at trying to produce artificial general intelligence or really powerful AI. I actually think these algorithms are the fastest path to producing AGI. I also, as I mentioned, I think open-endedness and AIJs are the next big wave in AI because with foundation models, open-ended algorithms can now stand on the shoulders of giant human data sets. And these are going to be great catalysts for our open-ended algorithms. That's true both for environments like Genie or OmniEpic, where you can generate environments in code using language models. It's also true for the agents themselves, which can pre-train and kind of come into the world already knowing a lot about how to act and how to explore, making them more quick to learn the next challenge and the next challenge and the next challenge. So one way to think about this is that evolution took 3.5 billion years to produce humans. And then humans in about 100,000 years produce all the marvels of human culture. big cities, skyscrapers, cell phones, computers, AI itself. So by combining VPT and SIMA pre-training with environment generation, we can like skip ahead to the interesting part. We don't have to spend 3.5 billion years of compute to get a brain. We can just skip ahead to like what happens once you have human type intelligence as the beginning of your algorithm. Then you can race ahead and invent new things. So with Omni Epic, we can finally produce what is interesting in a Darwin complete search space. That avoids the pitfall of trying to define what is interesting. That's basically really, really, really hard. And that allows profound opportunities for quality diversity, open-ended and AI generating algorithms. The AI scientist is the same set of exciting ideas, but applied to agents and science itself. So is the automatic design of agentic systems, but for AI. Agentic like wrappers and workflows. And then finally, I added thought cloning, which kind of is a performance lift also by training on human data, standing on the shoulders of giant human thinking data sets. That gives us higher performance, more generalization, more adaptability. It also gives you interpretability, makes it more easy to debug your systems, and also helps you with AI safety. So that is a lot, but you kind of see almost the main arc of my whole career in one big talk. So thank you for listening to such a long talk. It's been a pleasure to share it with you and have the time to do so. I want to deeply thank all of my collaborators, my funding agencies, and you for listening. I'm ready to take questions. Thank you.
Thank you, Professor, for your wonderful talk. And I'm gonna open up the audience for a last question.
Hi, Professor. Can you hear me?
I can.
Oh, okay. I've got a problem, and that is, as you mentioned, the backbone of your work is working on foundation models and using human data. I want to argue against this notion a little bit. Up until now, the definition of interestingness is really subjective. What we as human beings think is interesting. There are problems is interesting in essence. I guess this is what we would have to be, thriving for. We might label a problem as not interesting, but it may be in fact really interesting in essence. So don't you think that building up on our work on foundation models wouldn't limit us in some way? We would be biased somehow.
Yeah, great question. Couple things. One, bias is good. If you're not biased towards interesting, then you'll probably spin your wheels, endlessly stirring sand around and saying, hey, new pattern, new pattern, new pattern, new pattern forever. You do want to bias towards what is interestingly different. So I think that's probably a good thing. But you might say, hey, we might be biased towards what we currently find interesting. That will prevent us from recognizing new things that are interesting. I actually think that there's a pretty good chance that this is not going to be that big of a problem for a very long time. I don't think we know that AI is not very good at producing at handling itself out of distribution. So many people say, hey, if your goal is to continuously produce new stuff, soon you'll be out of distribution and your model of interestingness won't work very well. I think that may not end up being a very big problem for the following reason. What counts as interestingly new is conditioned on what has already been invented. Okay, so all I have to do is look at the stuff that just got invented and know if the next thing counts as interesting compared to that. So, for example, if I took somebody from the 1800s or the 1500s and I brought them forward to today, they would be blown away. They would say, oh my gosh, you have planes and you have television and you have cell phones and you even have jetpacks. This stuff is crazy. Wow. But after they took like a couple, days or weeks to like learn our technology, I still think they'd be able to predict the next, like to recognize that a new thing is interesting. Like the thing we invent next year, that's all the rage. They too would say, oh, given what you had up to 2025, the stuff that was invented in 2026, I see that is interestingly different. which is to say, you don't need the model of interestingness to just know if a new thing is interesting. You need to know if the new thing is interesting given this archive of stuff. And since you're constantly getting a new archive of stuff, all you need to do is this simple task of predicting if the next thing is interesting. So I think that function, the model of interestingness, will probably generalize way outside of the current distribution because it's a pretty interesting task to just say, given this, does this count as interesting? And that will go very far. Now, ultimately, in order to do that, you need to have features and understand the stuff that you're looking at. So once the technology is wildly different, once the mathematics are completely alien to us, maybe this starts to break down. But at that point, you've got a huge archive of innovations that you've invented to get to the point where you're now out of distribution. You could just fine tune and update your model. Just do like generative pre-training, just like typical internet pre-training, but on the archive you've generated, and that might get you farther and farther and farther. So this is an empirical question. I consider it the $1 trillion question, actually. I think it'll work really well, but we have to go do the science, and that's the kind of science that students on this call could go do.
Mm-hmm. So thank you very much, Professor. Yeah.
You're welcome. I see at least one more hand, but I'm not hearing anybody. Oh, there's some.
Hello, can you hear?
Yep.
Hear me?
You're coming in very slow, internet-wise.
Thanks for your great presentation.
I can still hear you. Go ahead.
Yeah, thank you for your great presentation. I have a question about your AI. Is my voice clear?
I think there's a pretty big delay. So you can try to ask your question and I can just see if I hear it. Or if there's a text chat, you can put it in text chat.
Hello. Hear me?
I'm going to recommend you type your question in the chat. I can see the chat if you want to ask it there.
Hi, can you hear me now?
Now I can, yeah.
Oh, I'm sorry. I have a question from your AI scientist paper. Actually, I just checked the first version, and I think that you use self-assessed methods to evaluate the quality of the generated ideas. I think that in other methods that they use tree search at the decoding times to increasing the creativity of the model, they use reward models, and I think there is a great risk of reward hacking in these kinds of using reward model for evaluating the quality of the generated ideas. I want to know, is there any better way, for example, getting feedback from the environment? Actually, I mean, execute that idea or experience it in the environment, in real environment, and use the real reward, and then fine tune with RL our models in a way to create better ideas. I think, is it applicable, or what do you think about this?
Yeah, so I think it's a great point. In fact, that's another answer to that I could have given to the prior question, which is in addition to everything I said, you can also periodically try stuff in the real world and see if it works and see if it's interesting. So, if you can get to Mars, then you've done something interesting, and you can kind of check that by looking to see if you got to Mars. In your case, in the AI scientist, I love your idea. We actually do that in V2 in terms of having a tree search and a value function that judges whether or not like the current stuff we're doing is helpful. You can also add in grounding it, and to some extent, our system is grounded. It's taking real experiments on real data sets, generating like actual loss curves and results, and it can look like, how did I do on this data set? But you still have the challenge of evaluating whether or not the results of the system are interesting and actually impressive. So just like a human scientist in a paper says, I'm trying to test this hypothesis, the right experiment for that hypothesis is to see whether or not I can improve performance on mini ImageNet. I trained on mini ImageNet and I got this performance, then and this performance is better than this other algorithm, and that matters in terms of confirming my hypothesis. I want to point out that there's a lot of subjectivity in that process in terms of, was it the right hypothesis? Was it the right experiment to test the hypothesis? Was it the right, did the result actually confirm the hypothesis or not? Is the baseline you compared against the right baseline? All of this is more than just an actual number. So yes, you can do real experiments and get real data, but it's still a subjective thing to figure out whether or not that data actually matters in the context of the original question that was being asked, let alone whether the question that's being asked is interesting. So science is subjective. This is why we have peer review. We don't automatically accept and reject papers at NeurIPS based on a number. You have to make an argument, and then humans judge whether or not your argument was good or not. And so it's a little harder than it sounds to ground it, especially if you truly want to let science go in any direction. If you just want to search for the best ImageNet result, you can just use a number. But our ambitions are grander than that. And so we inevitably will import this problem of human subjectivity to the process.
Yes.
Okay, somebody asked, Soban asked a question. Hi, Professor Clune. Thank you for the perfect presentation. Well, I don't think it was perfect, but thank you for the compliment. I have a question about LLMs and RL. I think RL fine-tuning of massive LLMs is computationally expensive. Are there lightweight RL methods, such as offline RL, parameter efficient tuning, or distillation techniques to make this process more scalable without sacrificing performance? Ultimately, first of all, I love this idea and this question. I think about this, like I've been thinking about this week in my lab. If we want to, for example, scale up OmniEpic and really see what kind of environments get created, the bottleneck is training the RL agent, even with pre-training. While that helps you then have some massive LLM, like a VPT model with 500 million parameters, fine-tuning that is expensive. Short answer is I don't know. We don't have a great option right now. However, you could try something like LLM policies, where the LLM is just spitting out actions, and so you're not training the weights of a model. But even then, if you're trying to learn new skills, then you'd have to fine tune that or rely on in-context learning. You have some other algorithms you suggest that could work. I actually think this is a great place for some researchers to try to figure out what is a way that we could get sample efficient learning without, like much more sample efficient learning. Voyager was an idea that was using an LLM to kind of be a policy, and that helped them. Or maybe we just have to wait for compute to make things cheaper. I don't really know the answer. This is a great place to research. I wish it wasn't such a bottleneck. I suspect in the limit that we need a giant model with lots of parameters to really accomplish a lot of our tasks. But how can we make that thing really sample efficient? Maybe with pre-training, maybe with meta learning, maybe with in-context learning, where it uses in-context learning to solve a problem, and then maybe it takes a few gradient steps on the solution to then get that solution into its brain. So efficient fine-tuning. This is kind of, I think, the frontier, one of the frontiers of AI right now that we need more work on, that people will make progress on. So let's go do some research. Ali Reza has a hand up.
Hello, sir. Can you hear me?
Mm-hmm.
First of all, thank you for your presentation. It was quite fascinating. And I was wondering if it would be helpful for us to kind of link similar actions that our agent can take together. For example, you had an example about a warrior in a field that could run or punch or do things like this. Maybe this warrior can also kick or do some other forms of attack. And would it be helpful for us to um, have some kind of categorization in our action state? And the same thing for our environment generation. You had an example about uh, a Minecraft world, which was very cool. And I was wondering if we reskinned the Minecraft world, make it look different, change the style and things like this. Could we have some sort of a concept of categories, like the concept of a chest, the concept of a village or something, so that even if it looks different, um, the model can recognize that two different environments are actually the same thing?
Sure. Yeah. I think basically you get that for free if you're training in a deep learning way. So if you're training a really big model to, act like in Minecraft, my guess is that the internal representation of the VPT model does recognize that doors are similar to chests in the sense that they can be opened, and it recognizes that um, an iron pickaxe is similar to a diamond pickaxe in that they are made in a similar way but with different ingredients, and they have similar properties, and that they can break stuff, but they can break different stuff. And so that walking around a lake in a forest is similar to walking around a lake in a sand desert world. All of that stuff, I mean, the magic of deep learning is that it will just learn all of that implicit categorization and kind of the relationship between concepts and features inside of its internal representations. I think the same thing is true in terms of acting. For example, in thought cloning or in SIMA or in VPT, because you're training on massive amounts of data, it probably in its own internal representations has the notion like, oh, I'm going to go forward and then slash is similar to I'm going to like go forward and then punch. But it knows they're a little bit different. And so the short answer is we want everything you want, but I don't think we want to try to hand code it. We want to learn it from data, and then all the magic will just kind of show up in the brain of the system.
All right. Thank you very much.
Thank you, Professor. I think we have a few minutes from our time. And for the final question, I just want to ask a question that if you were an undergrad or a starting graduate student today and wanted to start your career, and you have these curiosities about the nature of intelligence, what career would you choose? How would you go about uh, finding the answers to your question? Would you go to university, join a startup, or what projects you're gonna work on if you want to start today?
It's a good question. So I think that as an undergrad, the first thing I would do is I would like study as much as I can in machine learning. There's a great quote from Richard Feynman, which says, "That which I cannot build, I do not understand." And so I think the best way to learn about intelligence is trying to build it and trying to learn about humanity's efforts to build it. So learning about deep learning is amazing, and you'll learn so much about thinking and evolution and neuroscience and this just by studying deep learning and machine learning, and then trying to build models. I also think that I'm biased, but what I would recommend is trying to go into the research in open-endedness. Like, come join us. It's such a fascinating frontier of trying to not only create intelligence, but create a process that produces intelligence and ever increasing intelligence, just like Darwinian evolution did on Earth. It's so fun and fascinating. And I've been working on this for 20 years and have been fascinated in it for 20 years. But one of the craziest things that's happening for me in my career is this little tiny topic that like it used to be like me and like 5 other people cared about, or maybe 15 in the whole world, is now one of the hottest topics in all of AI. So at iClear this year, there are many tweets you can go see. Open-endedness is like one of the most popular topics in the entire conference. So it's being talked about in many different workshops. There was an entire keynote explicitly on open-endedness by Tim Rockdishell that I highly recommend you watch. And so this topic that I just told you about is one of the new next waves of AI that I think is going to increasingly become powerful and popular and exciting. So that's a good time as an undergrad to jump in because it's still pretty new and fresh. Not that many people are working on it, but I think it's got huge potential and it's just endlessly fascinating. In terms of startup versus academia, if you actually are interested in AI and learning about research and how the brain works and exploring new ideas, I actually don't think a startup's very good. You end up spending a lot of time raising money and arguing for why you're going to make money and dealing with clients and messy data and all. You don't get to just spend your time doing science. That's a total fantasy. However, I do think that industrial research labs are not too bad if you can join them, like an OpenAI or a DeepMind or whatever. You still end up with some businessy stuff, but for the most part, you get to do a lot of science with a lot of resources. But to get that job, you need, at this point, you need a PhD in AI and machine learning, really. I mean, some people go direct, you can try, but I just recommend like get an undergrad in ML and then get a PhD in AI and ML, do really wonderful work, and then you can either become a professor or you can join an industrial research lab, and you can do a lot of great things in either place. But just like more deep.
Thank you, Professor, for this great answer. I just wanted to once again thank you for accepting our invite. I tried hard to reach you, and I'm very glad.
I gotta give you credit. You tried many emails and Twitter, and like people came up to me physically at the conference, so it worked in the end.
Thank you, thank you.
You're welcome.
It was an honor. Thank you, and have a good rest of the day.
All right, enjoy your class. Thanks, everybody.
Bye.
Bye.